It's good to be able to continue with you. Today we get to introduce really the last type of integral we'll get in all of our calculus. We're going to start talking about surface integrals. So we've had definite integrals and indefinite integrals and improper integrals and just about every type of integral that you can imagine. Most recently, we were learning about line integrals as a means of calculating the flux and also to find the work and the circulation. And here we're going to learn about surface integrals. This is sort of the general bit, if you will. The section that we're going into is analogous to 17.2, where you learned about line integrals. And so you learned about line integrals, and then you used them. You learned some cool tricks later on with the conservative fields and the fundamental theorem, and then again Green's theorem. So it's like you learned about line integrals, and then you did stuff with them. Here we're going to learn about surface integrals, and then we're going to do stuff with them as well. Let's see. So that's kind of where we're going. So we've been studying integrals on intervals on the real line, on regions in the plane, on solid regions in space, and along curves in space. And so one situation is still unexplored. And so here we are in 17.6. So suppose, for example, a sphere has a known temperature distribution. Perhaps it's cold near the poles and warm near the equator, like the Earth. How do you find the average temperature over the entire sphere? I think about this as being somewhat relevant in the context of all of our climate change things. It's like you're like, well, it's warmer here. Well, it's colder there. So how can we tell? Well, we need to know kind of the overall average temperature. So how do you find the average temperature over the entire sphere? In analogy with other average value calculations, we should expect to add up the temperature values over the sphere and divide by the sphere surface area. Because the temperature varies continuously over the sphere, adding up is going to require an integration. So how do you integrate a function over a surface? And so this leads to the idea of a surface integral. All right, so let's look some more at the surface integrals. And again, this is section 17.6 on surface integrals. And we've got 2 days on this. One of the things that tends to be challenging in this particular section is understanding parameterization in this context. And so we're going to spend most of our day today deriving and setting up a formula, and then we'll spend tomorrow doing more of the crunching. So there's not a lot in the way of crunchy or math examples today. Mostly it's going to be pictures. And I'm hoping we'll be able to end with an example of our first surface integral. All right, so it helps to keep curves, arc length, and line integrals in mind as we discuss surfaces, surface area, and surface integrals. What we discover about surfaces parallels what we already know about curves. It's just all lifted up or raised one dimension. And yes, within a couple weeks, you'll finally get your Sunday nights back. So woohoo, Jason and others. So here's the parallel concepts. So arc length is sort of parallels the idea of surface area. Line integrals kind of parallel the idea of a surface integral. And with curves and line integrals, we've always parametrized with just one parameter. And now we're going to have 2 parameters because we're going to be up 1 dimension. So in this section, we're going to start by talking about surface integral or parametric surfaces. Then we'll talk about surface integrals. And then lastly, we'll deal with this across a vector field. So a curve in R2 is defined parametrically with R of t equal to x of t, y of t. What I want you to see here is that there is one parameter. So one parameter, 2 dependent variables, namely the x and the y. So stepping up 1 dimension to define a surface in R3, we will need now 2 parameters, and there will be 3 dependent variables. So the most common parameter choices will be u and v. You could also choose s and t. You could choose r and theta. There's lots of choices, but these are the most common ones. So the common parameters will be u and v. and then our dependent variables will be the x, the y, and the z. So let's look at our first manipulate. Okay, so we have this 3D surface that we've generated here, and what I want you to notice is that for any particular UV, we pick the UV, and that will determine this position vector going from the origin up to the surface. And so if you want to generate a surface over here in R3, we're going to need two parameters, U and V, and we've got to let them range over some sort of a region. You'll see later on that a rectangular region in UV does not necessarily correspond to a rectangular region like this one seems to be. This one seems very rectangular shaped in 3D, but it gives you some idea what's going on. Couple things to note. So notice that you can hold, we could hold V constant. So if we held V, then it would be like letting our U change. And so notice we're staying on that same blue line, and holding U constant would be like staying on the green line. And so you can see how I think you can see that having a single parameter, whether that's getting rid of U and V or simply holding one constant, would be the same as creating a little space curve. So questions for how a rectangle in UV would, in the UV plane would be mapped onto the surface in the X, Y, Z space? Very good. All right, so this is a general example. What I'd like to do next is to look at some famous examples. So we're going to make the assumption that the parameters vary over a rectangle. So we're going to require our UVs to live in a rectangular region, but the output won't necessarily be rectangular. So as the parameters UV vary over R, the vector RUV equal to X of UV, Y of UV, and Z of UV will sweep out a surface S. Okay. So just to help you with this color coding, notice that R is going to live, this is where the world of the parameter. It's the parameter world. And then S, this is our 3D world. So if you think about what you would graph, typically you graph S, you graph the S, the surface. You can't usually see the parameter. Parameters are sort of behind the scenes. Sort of like time isn't visible, but you can see the XYs that come out when you put in a time value in earlier parameterizations. So let's look at these various examples. So first, how would we use two parameters to parameterize a cylinder? So here's a cylinder, comes out. And what I want to point out to begin with is that the region in our UV world, so here's UV, the region in our UV world is a rectangle. And what is that rectangle? Well, it looks like our U's are going from 0 to 2 pi, and our V's are going from 0 to 2. So rectangular region for the parameter, cylindrical output. How does this work? Well, if you basically you pick a height, so if we pick some height and we travel along our U, we'll travel all the way around the circle. Then choose a new height, travel all the way around the circle. Travel new height, travel all the way around the circle. So this would be letting V be fixed and letting U vary. You could also go the other direction and say, pick an angle and then look at what happens across all those heights. Pick a different angle. So in one way of thinking about it is this is like a whole bunch of concentric circles that are together forming the cylinder. The other way of doing it, thinking about it, would be, oh, it's just a whole bunch of vertical lines that if you draw enough of them will form a cylinder. The formula here, this is going to shock you. Notice that we have the cosine u, sine u in our x and y component. So this is giving us the circle part. The a's, what are those a's doing?
It's your radius.
That's telling us our radius. And then the v is what's going to give us all the heights up and down. So it's like create circles in the XY world, and then for each point on that circle, create a vertical line, and that's what's happening with that V there in the Z component. Questions about using, about how you create a parametric cylinder or represent a parametric cylinder, at least a vertical one?
Quick review.
So quick review is that if you want to create a parametric surface, so this is a parametric surface, then you're going to need two parameters. And our two parameters are going to be U and V. And we want to have a cylinder, so we need to have some circleness to it. So we have our cosine U and our sine U. So this gives me the circleness in the XY plane. I want to be able to adjust my my radius, so I could put an A out front. That'll adjust the radius. We're not going to choose R because we already have an R in the question. And then we want to allow for to bring it out of the two-dimensional circle world and turn it into a cylinder. So we're going to add a second parameter, that second parameter, which is going to make it so that our output is a two-dimensional surface, like a two-dimensional surface instead of a single dimensional space curve. That help, Titus?
Yep, sure did.
Very good. Other questions about this? Very good. All right, so that was a cylinder. Again, notice a rectangular domain. Let's look at a cone. So here you can think about a cone as having sort of two shapes happening. You have those circles that are happening at various heights, and then you could also think about there as being a whole bunch of different lines kind of all going through the origin that are coming out. And so here you can see the sine u, so cosine u and sine u. So that's going to give you the circle part of the cone. But we no longer want to have a constant. We no longer want to have a constant radius. We want the radius to vary, And so there's this term out front that's going to influence the size of these circles that are here. And notice that there's a V parameter in that radius that's tied to the height. So basically, we figure out what height we're at. That tells us the radius of the circle.
And the height is constant, right?
Say again?
And the height is constant?
The height and the height would be constant, correct? And the A would be constant as well in this context. So, again, you can see if you let the U's vary, we get circles. Choose a different height, you're going to get a smaller or larger circle, different circle. If we let the V's vary and kept U constant, notice we're going up like a line. It's a little hard to keep the mouse constant. And the A, what the A is doing is it's changing the steepness of the cone. Okay. So key concept is that if you have a space curve, how many parameters do you need?
2.
Space curve versus surface.
Space curve, you need 1, right?
You need just T. And for a surface, you need
U.
2.
U and
Here
V.
you need U and V. And so here this T could either turn into an XY or it could turn into an XYZ. At least graphically, our UV is going to turn into, is going to always turn into an XYZ. I mean, it's not that you couldn't have it live in 4 dimensions, but that's a little harder to draw. So, phrased another way, if you have 2 parameters, then you know you have a surface. If you've got a surface, then you know you need to have 2 parameters. This is the counting part of the class. Okay. Questions about this?
In this question, or in this shape specifically, is A the gradient of the slope?
Is A the gradient of the slope? I don't know. Well, so here we would need to find our X, our Y, our Z, right? Like well, that's kind of weird. Not that. It's where we need to find FX. I'm just trying to think about that. The gradient of the slope. You have a gradient of a potential function. So this, I think the answer, as I think about it a little bit more, I think the answer is no. Because I think the answer is no. What would the gradient field look like here?
Looks like a constant if you ask me, though an increasing constant.
Imagine if you were on that blue line or that blue circle. So here's this blue circle here. What would the gradient look like? Which direction does the gradient point?
Down to the center.
Gradient always points in the direction of what?
The steepest change, isn't it?
Steepest, which kind of change? Up or down?
Up.
Up. Yeah. So it's going to be pointed out. So it'll look kind of like the spiky ball thing from yesterday that you guys were razzing me about. So I think does that make sense that this would be what the gradient would look like? This is the gradient of that surface. So this is the gradient field of S. Questions about that?
Makes sense.
Answer your question then?
Almost.
So,
And so in this case, like practically the gradient field depends on the value of V or the limits of V, right? Because that's the height.
I think that the gradient will be, because the slope's going to be the same everywhere, I think that the gradient will be the same everywhere. But it's definitely going to vary with where you are on the, I mean, the gradient is good. I think it'll be the same everywhere along a line through the origin. Because the slope's the same everywhere along a line through the origin. But you have to figure out which, it's really going to depend upon this angle U. So as soon as you pick the U, then you're going to know what that gradient is going to be.
Yep, makes sense now.
Good, good. Cool. So one thing I want to point out as we wrap up is notice that this rectangle is going from 0 to 2 and 0 to 2 pi, same as the last rectangle, right? These are the parameters. They live sort of in a different world than the actual surface. And so those parameters 0 to 2 pi, 0 to 2, in the previous example gave you a cylinder. Here they give you a cone. Frankly, I would prefer a cone filled with ice cream and then maybe a cylinder filled with coffee or something like that, assuming we can put a bottom on the cylinder. Let's look at one more example. Well, more than one more example, but one more famous one. So here's a sphere. Again, the A, so that A that's out front, A, that's going to be the radius. Why do we use A instead of R to describe the radius?
Because we already have our UV.
Yeah, we already have an R, so ARG, we have used up our R, so let's use A. It's like a shout out to Canadians or something like that.
Or the homies,
A. So here's our sphere, notice that we're using, or our parameterization is based on which type of coordinate system? You see this?
cylindrical.
Yeah. So do you see that? Exactly. So do you see the A cosine V, A sine V? So that's like the R cosine theta, R sine theta. And then there's we had sine phi, A cosine phi. Except for phi and theta are so yesterday, now we're using U and V. Took me a long time to figure out what was going on here, and then one day it finally clicked. I was like, oh my gosh, this isn't that hard. It's just the same thing as spherical coordinates. Notice here those what our rectangular varies between. So our U's are living between 0 and pi. And so those u's, those were in the old days, in our spherical coordinate days, those would have been our phi's. And then our a's, sorry, our u's are living between 0, wait. I just said that. Did I say this right? Okay, let me back up. Our v's are living between 0 and 2 pi. And in the old days, we used to call v theta, if that helps you. So it's kind of funny. You have a rectangle here, and that rectangular domain of the parameter translates over here to the surface of a sphere. Surface means you're going to have 2 parameters. Questions about this one? Let's focus in on the shapes. So if we hold our v constant, we're getting those blue lines that are being swept out right here. Okay, that's nice. And then if we hold u constant, then we'll get the circle all the way around the like a line of latitude on the globe. All right. This isn't how to say it. Like the good news about parametrizing surfaces is that other than some really straightforward examples like cones and planes and spheres, usually the parameterizations are so challenging for us that we don't need that they either have to be given to us or we would, I don't know, hire somebody to figure it out for us. So you don't have to worry about having to come up with a whole bunch of parameterizations on your own. But it's good to have some basic examples in mind. Let's look at one other really famous and powerful example. So suppose you have z equals f of xy. And so there's some surface here. And so you got some surface f, and we want to parameterize the surface because we're going to be using a line integral. So what would our parameterization be in this particular case? We have r of uv equal to what?
UV F UV.
So let x be u, yeah. And then y would be
V
v, and then z,
F UV.
f of uv. Or sometimes students start thinking, you know, there's just too many letters in this world. I want to conserve my letters. And so you could also do the same thing by parameterizing instead of using u and v, you could just parameterize with x and y. And your first coordinate is going to be x. Your second coordinate is going to be y. Your third coordinate is going to be f of xy. So this is the one instance where you may well need to come up with your own parameterization, is if you're given some function like z equals f of xy, and they say, hey, I want you to evaluate a surface integral, well, then you could just parameterize as follows. Questions about that? Very good. Let's see how we're doing on our notes. All right, so surface integrals. So we now develop the surface integral of a scalar valued function f on a smooth parametrized surface S, described by the equation r of uv, where the parameters vary over the rectangle R. So the functions x, y, and z are assumed to have continuous partial derivatives with respect to u and v. So the rectangular region R in the uv plane is partitioned into rectangles. And let's look at the manipulate. Okay. So what I want to start out by pointing out is that each little sub rectangle on the parameter in the parameter world corresponds to a region over here on the surface. And we're going to name each one of these regions here. We're going to name each one of these a patch, like a patchwork quilt. And so you can imagine that this whole thing is made up of a whole bunch of patches. So in this case, there would be 9 rectangles in the UV world, 9 patches on the surface. If we want to find the surface area of the overall surface, you can imagine we're going to find the area of each of these individual patches, and we're going to add up those areas. If we want the area to be more exact, then we could increase the number of divisions. So more U divisions is going to give us more rectangles in the U direction, more rectangles this way, more patches. We could also increase the number of V divisions. And as you can see, the more patches, the better approximation for the actual surface we're going to get. This book does something a little bit interesting. Rather than doing a double, usually in the past when I've seen this in other texts, we've ended up with a double sum. So you end up with I's and J's, and there's lots of letters running around. In this particular case, they sort of simplified it, and they simply said, let's just assume that our numbering system, finishes one row out and then picks up on the next row. And I think it's I don't know whether it's a good move or a bad move, but it's kind of an interesting move that the text chooses to make. Are there any questions about how the rectangles on the UV side connect to the patches on the surface side? Very good. All right, so what are we going to do with this? Well, what we're going to do is we're going to play a clever little game. So to construct the surface integral, we are going to define a Riemann sum which adds up function values, maybe the temperature at a point, multiplied by the area of the respective patches. And so this, you got to be a little bit careful here. Notice there's a delta S, and you might think to yourself, wait a second, we've done delta S before. Ah, but you thought we did delta S before we did delta little s. Ooh, we did delta of little s. So in this case, it was referencing surface area, or not surface area, it was representing arc length. Whereas in this case, we're talking about surface area. So big S, surface area, little s, arc length. Sorry, you got to keep them straight. There's just not enough. It's just not enough letters in the alphabet. Twee, it's okay. We can use multiple patches if we need to fill in all the holes in understanding. So good news. Okay, so we're going to find some function value, and then we're going to multiply by that surface area of the patch. We got to find that surface area of the patch. And so let's look at our, I think our 5th manipulate for the day. Nope, this isn't the right one. This one. Okay. So what color is the patch here?
A couple
yeah.
patches, I think 6.
Yes, the patch is this blue part here.
So the patch is only like one. You can't say like multiple patches. It's like,
That's true. There's one blue patch and 8 yellow-orange patches.
okay.
But let's just focus in on the blue patch.
Okay.
So we want to find, good call. So we want to find the surface area of this blue patch, but patches are way too complicated for us. So rather than doing complicated stuff with patches, what we're going to do is we're going to focus in instead on this shape here, which is, anybody know the shape? It's not a it looks a little like a rectangle. It's not a rectangle. It's a
Parallelogram.
Parallelogram. I finally learned to spell parallel because I realized that right in the middle of parallel, there was 2 parallel L's, and that helped me. So the way we learn things. So we're going to say that the parallelogram is approximately equal in surface area to the patch. So we're going to try to focus in on what's the area of that parallelogram. Let's see. So a little bit challenging to see. There's a lot going on here. But notice that here we picked a point here, P, and at P, X5, Y5, Z5, we have that one point on the patch. And at that point, we found the tangent going in the U direction. So this is the tangent in the U direction. U direction. I think the T here would be for tangent. So the tangent in the U direction. And then we got to ask ourselves, how far in the U direction do we want to go? We want to go a length of delta U. And then we also have, I think it's I said a tangent, I think I want a unit tangent, if I remember right. Unit tangent in the U direction, and then we're going to have a unit tangent in the V direction over here. So that will give me my other side vector. How do we use those two vectors to find the area of the parallelogram?
Cross product.
Cross product, right? So this area here would be the cross product of the two. So it's going to be 2 delta U cross TV delta V. So this will give me the area of the parallelogram, which would be approximately the area of the patch. Questions about that derivation? Very good. I think it should be clear from all the calculus that you've done that if we increase the number of patches, that's going to decrease the size of the parallelograms, and our parallelograms are going to get closer and closer to our patches. Let's see if I can add more divisions. So notice if I max it out on the animation, notice the difference between the parallelogram and the patch is pretty small. So yay for patches, yay for parallelograms, yay for calculus. Okay, so back to the derivation. Nice, Enrique. There you have your VW Beetle. So the area of the parallelogram is the magnitude of that cross product, because the cross product itself is just a vector. And so in order to do this, we're going to need those two special vectors. So we needed the 2 vector TU, and so that's the vector tangent to the surface corresponding to a change in U with V held constant. Other books would use RU, but the formula for TU is the partial of R with respect to U. Formula for, ooh, that's nice. This should say TV. Formula for TV is the partial of R with respect to V. So there's a whole bunch of like a fine print, like of kind of working through the derivation and how do you figure out what these delta U's are, the delta V's. But I think I want to just focus in on the main point. And so the main point is that if you want to find the area of a patch, right here, here's that area of the patch, then you look at the cross product of those 2 tangent vectors and you take their magnitude and you multiply it by the 2 changes in U and change in V, the delta U, delta V, which is pretty straightforward. So at the end of the day, we arrive at this formula where the the surface integral here is equal to a Riemann sum. And notice here, it's a Riemann sum, and I actually have 2 different things going to 0. And that's trying to capture the idea that we went from all our patches along one row, and then we skip to the next row, and then we skip back to the next row. So that's what's going on there. That's why you have the double delta U and delta V going to 0 taking place. So this all leads to our final definition, which is that the surface integral can be evaluated by evaluating the function f at all the x's and y's with our parameterization, and then multiplying by the magnitude of TU cross TV, and all this is dA. Questions about that derivation? Very good. One really important but simple note is as follows. Notice that if your function equals just 1, then you're going to get out the area of the surface. And so we're pretty used to this. If we had a double integral with the integrand 1 back in chapter 16, then that would represent area. If we had a triple integral, it would represent volume. If we had a 1 in the line integral world, it would give us arc length. Here, the 1 will give us the surface area. So just a little side note. So there's not enough time to work through this next example, so let's simply hit some of the high points and then we'll work through the details tomorrow. So here's the high points of this next example. Notice the steps end up being the same. Step 1, parametrize. Step 2, find that differential element. What's step 3 going to be? Step 3, thank you all for not answering that question. Step 3 was substitute and integrate. So it's this, notice the same process that we use for line integrals all the way around. Parametrize, find your differential element, substitute and integrate. So here, just like I predicted, we've got the parameterization is given. In order to find the differential element, we've got to find TU and TV. To do this, remember that TU is just the partial of R with respect to U. And TV is just the partial of R with respect to V. Once we've got them, we find their cross product and we find the magnitude of the cross product. So let's parameterize. All this gives you your, so this would tell you that ds, and this is big S, would be 1 plus u squared du dv. And then we're going to just substitute in. So we take that ugly surface integral. Here it's in terms of S, the surface. Over here we're writing it as an iterated integral, but now we're working across the region R. And so your X is going to become U cosine, your Y is going to become U sine, U is the Z, so this is all the X, Y, Z from before, and then all that stuff there at the end becomes your DS. At this stage, it's just about integrating your way through, just a whole bunch of writing. So that's the basic gist. We'll work through the details of this one at the beginning of class tomorrow. But that's your introduction to parametric surfaces and surface integrals. Thanks everyone for another good day. If you have questions, feel free to stick around. I'd be happy to work through them at office hours. But have a wonderful day. Have fun with your Green's theorem homework if you haven't finished that already. And I look forward to seeing all of you tomorrow. Take care.
Yeah, Dusty.
Bye, Dusty.
Take care.
Hey, Dusty. Oh, sorry. You go first.
Sorry, you go.
Mine has nothing to do with math.
Okay. Well, I've got a question about the homework.
Okay. You want me to pull it up?
Sure.
Let me stop the recording first.